Hello and welcome to the example video for hypothesis testing. So today we're going to talk about a bunch of different hypothesis tests. Well, 3 to be more specific. I'm going to adjust my mic, which should be mildly annoying, sorry. There we go. Okay, so the big thing about hypothesis testing is we want to make sure we form the beginning part of our question correct. We want to make sure that we have the right claim we're trying to test and we determine our null hypotheses well and our alternative well, because if you get their correct null and alternative, when you calculate your p-value, you'll go the right direction and you'll know which test for proportions you should be using. So the big thing is I make sure that I do my null and alternative first before I proceed to the rest of this process, because if you have the wrong null, you might have the wrong alternative, and if you have the wrong alternative, then when you go to calculate your p-value, you'll calculate the wrong one, and then you'll make the wrong decision. No! Okay, so we're going to focus on that. The other thing we're going to focus on making sure we choose the right formulation to give us the correct test statistic and the correct p-value. So the big thing is that we have only one test for proportion, so that should be pretty easy. Once you know you have a proportion, we should be using the one sample p or the one proportion test. And if you have a mean, you should be using either the z or the t. And remember, the end all to be all of if you should use the z or the t is if you know the population standard deviation sigma, you should be using z. And if you're using s, aka the sample standard deviation, you should be using t. If you're having a hard time remember this, remember s and t are closer together in the alphabet. Oh yeah. Believe it or not, that actually helps me. It's okay. Anyway. And then we're going to make our initial conclusion and then state our conclusion. This is usually called the decision step, is number 5, and then step 6 is really technically your full-on conclusion that you would share with like your coworkers if you were their stats guy or girl. So here we go. Let's do some examples. Sorry if the scrolling makes you dizzy. Alrighty, so first up, we're going to be looking at some hypothesis tests. So we're just going to form some hypotheses and determine what type of test we should be using. Okay, so according to the U.S. Census Bureau, about 11.8% of registered births in the United States since 2000 were to teenage mothers. A sociologist claims that the percentage has actually decreased since then. Aha! We have a claim to test. The claim is actually that it's smaller than 11.8%. There's our claim. So we form our null, which is a statement about equality, and we perform our research or alternative hypothesis as the claim that we're going to look to test. And since this is looking at proportions that are smaller than 11.8, sorry, we're looking at things to the left of 11.8, and hence this is a left-tailed test. All right. Number 2. According to the Federal Housing Finance Board, the mean price of a single-family home in October of 2003 was $243,756. A real estate broker believes that because of the changes in interest rates as well as other economic factors, the mean price has increased since then. I actually would have thought it decreased since then, but we'll see. Anyway, so his claim is that it's increased, so we assume we are looking at this and thinking, oh, he thinks it's going to be greater. So our claim is that the mean price, this is going to be a mean test, is going to be actually larger than the stated amount, which I'm not going to read out loud again. So that tells us there's our research hypothesis, aka our alternative, and then our null is always a statement about equality because that we can actually build a distribution on. And since we're looking at things greater, or to the right of that number in particular, we are doing a right-tailed test. Okay, according to the Statistical Abstract of the United States, the mean monthly cell phone bill was $49.91 in 2003. Wow, I wish I was still paying that amount. Okay, sorry. Researchers suspects that the mean monthly cell phone bill is actually different today. I was suspect it's higher. Okay, well, they think it's different. That's enough. Okay, so their claim is that they think it's different. Remember, different we think of as not equal to. It's not this. It's not the same as, because we usually read is as equal to and same as equal to. So different is not equal to. It's the opposite. So that's our alternative claim that we'll be testing. And our null is a statement about equality because that we can build a distribution on and therefore actually do probabilities on. And since their alternative is a not equal to, this is going to be a two-tailed test. Yay! All right, on to step 2. Or problems 4 and 5. So for claim number 1, the null hypothesis is rejected. Oh no! Sorry, the claim made it number 1. So if we end up rejecting the null, then our evidence points more towards the alternative. So if we reject the null hypothesis, then there is evidence to support the claim that the percentage of registered births as teenage mothers is now less than 11.8%. It's pointing towards the alternative. This is a little non-committal though, because remember, not guilty isn't the same as innocent. Um, if we make claim number 2 and we reject the null hypothesis, we'd be saying that, oh, it's not actually equal to that, and our evidence points towards it's greater. So we would fail to reject. Is not rejected. Oh my gosh, I got that wrong. I was reading the wrong thing. So if we fail to reject the null, we're like, okay, I can't prove that this is not true. It's cool. So we would say then there is not evidence to support the claim the mean house prices have increased from 2003 value of $200. I cannot read that number well. $243,753. So, I mean, again, this is weird because it's not guilty, It's strange, but that's how we read it. It's cool. All right. So, let's suppose we look at a full example. So we suppose we have a simple random sample of 1,088 adults between the ages of 18 and 44, and it's found that 261 of the 10,088 smoke. This is based on the national data from a National Health Survey interview survey. Words. We used the 0.05% significance level to test the claim that less than a quarter of adults smoke. So there's our claim. So our null hypotheses will be that this is actually equal to a quarter, and we're going to test the alternative that it's smaller. Since this is clearly a proportion, we're looking at some defined success out of our sample. We know that our p-hat is going to be about 24%, which is pretty good. So I'm not going to be doing a z, not going to be doing a t. I'm dealing with proportions. I'm definitely doing a p. So my rejection rule is that if my p-value comes out smaller than 5%, then I will be rejecting. If it comes out bigger, then I will be failing to reject. So first thing we're going to ask ourselves, what our test statistic and what's our p-value? So I'm going to use Minitab to do that. So we're going to go to Stat, Basic Statistics, and down to the one proportion test. Click on that, and I'm going to change this to Summarize Data. The number of successful events I have is successfully viewing that you're a smoker, as successful as that might seem. And then my sample size is the 1,088 people. I'm performing this test against 25%. Because this is my hypothesized proportion. This is coming from my null hypothesis. And then I'm going to go up and hit my options. And I want to make sure that I'm using the normal approximation, because this is binomial in behavior. And then the other thing is I'm going to look at this and be like, oh, well, my alternative is actually a less than. So that's what I should be using. Okay, so we'll hit OK, and then OK again. And then notice that this produces not just our z-value, which is our test statistic, but our sample p-value. So there's our test statistic, and then there's our p-value. So if you look at this, our p-value is very large. It's actually bigger than our alpha, so we would fail to reject. So we'd say that there's not sufficient evidence to support the claim that less than a quarter of adults smoke. Yep, the claim has not been supported. All right. Let's look at example number 2. When planning for constructing a parkway, engineers must consider the weights of the cars to be sure that the road surface is strong enough. A simple random sample of 32 cars, yields a mean weight of 3,605.3 pounds and a standard deviation of 501.7 pounds. That's a big standard deviation. We use a 0.01 significance level to test the claim that the mean weight of cars is actually less than 3,700 pounds. Woof. Anyway. So as we look at this, our sample value has been given to us. Be careful. So there's two means floating around in here. One about the claim that you're trying to test, and one that comes from your sample. Remember, your sample is always a part of your evidence, not your claim. That's you trying to provide evidence for or against the claim that's been made. So it should never be a part of your claim or your null hypotheses. So I state the claim that we actually think it's less than 3,700. And so that will form my null and my alternative hypotheses. The big thing here is that I have a sample standard deviation, so that I will not be able to use a z-test on this. I'm going to be using a t. And then we notice that if our p-value is small enough that it's smaller than 1%, then I'll be rejecting my null hypothesis. If it's larger, then I will fail to reject my null hypothesis. So let's perform our test. So we're going to go over to Stat, Basic Statistics, and then over to one sample t. We're going to change this to summarize data since I don't have the data here in my, my worksheet. So my sample size is 32 cars. My sample mean I found earlier, 3605.3. And then my standard deviation, 501.7. And I'm performing a hypothesis test against the hypothesized mean of 37. Ooh, not 37,000, 3,700. Woo, that would have been bad. I'm going to go to my options and make sure that my alternative is correct. It is not, so I need to fix that. And it actually doesn't matter confidence level on this right now, but that's okay. And then double check. Okay, we're good. Alrighty. So there's my T, negative 1.07, and there's my P, 14.7. So this is about 14.7%. That's pretty high. It's pretty likely, which means that my evidence is likely to happen if the H naught is true, which means I'm not going to be able to reject it. So there is not sufficient evidence to support the claim that the mean weight of cars is actually less than 37,000 pounds. It might be more than, or even that value itself. Alrighty. So one survey showed that among 785 randomly selected subjects who completed a 4-year college degree, 4 years of college, reading, 144 of them smoke. Use a 0.01 significance level to test the claim that the rate of smoking among those in 4-year colleges is less than 27%, the rate for the general population. Aha! So we're seeming to test, is education and smoking related? I'd love to see this in a different country. Bet you that's interesting. Anyway, so our p hat is simply the fine success of yes, I smoke, and that's 144 out of the 785. So that's my p hat, my sample, not my claim. Remember, claim is actually stated somewhere else, and it's a statement about the population. So 37% is the rate for the general population, and I think it's actually going to be less among those with a college degree. So I want to test the claim that my proportion is actually smaller. And so I've got my null, which will be the equal to statement, and my alternative, and then I have well, clearly this is a proportion. That's our only choice for this. So we'll reject if I come up with a p-value that's smaller than 1%, and we'll fail to reject if it's actually bigger. So let's go on up to stat, basic statistics, down to one proportion, and let's put in the value, 144 out of 785. And I'm testing this against 27%. I go hit my options, and my alternative, it's smaller than 0.27. Okay, normal approximation, 95%. Off we go. Said okay. Whoa, that's a big Z. Big is relative. Big in size, you know, beyond 3 is big. So negative 5.46. So it makes sense that this is very small. If you're having a hard time on how I recognize this was going to be off the wall or off the charts as far as large goes, remember 3 standard deviations away from the mean makes up 99.7% of your data. Once you get 3 away, so since this is 5 in the left direction, so it's 5 away-ish, a little bit more than 5 away, you can expect this to be pretty much nothing. It's so small that Minitab is reporting that it's 0. Your computer say 0, mean very tiny. Okay, so as you look at this, that means we're super going to reject because our p-value is very, very unlikely. It's not very likely that you should get such a small probability sample by random chance. Therefore, we are definitely going to be rejecting. We say, hey, there's sufficient evidence that we can support the claim that the rate of smoking among those with 4 years of college is actually less than the national average or the general public rate of 27%. Woohoo! We're making conclusions today. In a study that affects prenatal cocaine use on infants, oh, such depressing things. If you're wondering where I get these, it's random studies, and sometimes they're sad. The following data was obtained for weights at birth. With a sample size of 190, the mean weight was 2,700 grams with a standard deviation of 645 grams. I'm looking at this and saying, oh, that's a sample standard deviation. I wonder if this is going to be a T. Use a 5% significance level to test the claim that the weights of babies born to cocaine users have a mean that is less than the mean of 3,103 grams for babies born to mothers who don't use cocaine. I'm trying not to get sad about this. So our claim is that the mean weight is actually smaller for cocaine babies. So there's the one from the sample, there's the one from the population, so that's the one that makes it into our claim, and therefore here is our null hypothesis and our alternative, and as we've already said, I don't have the population standard deviation, so I'm going to end up using the sample standard deviation, S, which means I have to use T, S with T. Okay. So if my p-value is small, as in less than 5%, I'll be rejecting, and if it's larger than 5%, then I will be failing to reject. Let's get our test statistics. So we're going to go to stat, basic statistics, one sample t. I'm going to use summarized data again. Here my sample size is quite large. My sample mean is not quite large because it's tiny babies. A little bit depressing, 645. And then I'm doing this against that claimed value of 3,103 grams. I'm going to check my options. And remember, we think that our mean is going to be smaller than that hypothesized value of 3,103. I'll hit OK, and then OK again. And then, oh my gosh, I'm getting very large values today. Okay, so our test statistic is negative 8.61. Blah, blah, blah. And then our p is also very, very, very tiny. So we would reject the notion that the babies that had prenatal cocaine use actually had the same mean weight as the ones who, didn't, or just the general ones who don't use cocaine. So there is sufficient evidence to support the claim that babies born to cocaine users have a mean, I should say mean weight here. I should have mentioned the weight because that's what we're actually testing this on. That is less than 3,103 grams. Sorry, that's a mistake on my part. That should have the word weight in there. All right. Bye, sad babies. See if I can get myself together here. In a survey, 1,864 out of 2,246 randomly selected adults in the United States text while driving. Okay, I admit that I've done this. They think that it should be illegal based on the Zobi International data. At a 5% significance level, test the claim that more than 80% of adults believe that texting while driving should be illegal. Don't judge me. Okay, so there's the stuff from our sample. That's going to make our p-hat. I'm testing, hey, I think it's more than 80%. There's my alternative. I'm sorry. There's my claim, which I'll use to make my null and my alternative. Remember, the alternative goes right along with the claim, and my null has to be a statement about equality in order to get a distribution. Clearly, these are proportions, so this will be a p-test. Anytime you get something out of something, you're going to end up p-ing on it. All right, so when the test statistic, I need to calculate these, don't I? I'm getting a little slap-happy about this. I need to lay off the cold medicine. I still sound very awful to myself. I wonder how I sound to you guys. I wonder, I'm talking to no one. That's what makes me sad. Oh, crap. So we need to do stat basic statistics one sample proportion because there's only one proportion test, thankfully, in stat 1. If you want to take stat 2, there's one more. That's like it. Well, there's kind of a third one, but it looks different. Anyway, so we have summarized data. Number of successful events I have is 1864, which sounds like a year. So it is 2246. In 2246, the robots need the humans again. I need to stop narrating. All right. From my null, I'm getting 80%. Got to go to my options. I'm looking at 95%. Ooh, I need it to be greater than. Go that way. Normal approximation, check. We're doing good. Let's hit OK twice. There is my test statistic, my z-value. And then my p-value. Woohoo! All right. Very tiny p, very large z. Definitely going to be hitting rejection land. So it appears there's sufficient evidence to support the claim that more than 80% of adults believe that texting while driving should be illegal. Darn it. I guess I got to rein that in a little. My husband does it constantly, though, so that'll be hard. Anyway. An energy official claims that the oil output per well in the United States has declined since 1998. The level of 11.1 barrels per day. That was read terribly. All right, his random sample is about 50 wells throughout the United States and determines that the mean output is actually 10.7 barrels per day. Assume that the standard deviation of 1.3 barrels per day. Ooh, we have the standard deviation. At a 5% significance level, test the researcher's claim about the mean oil output per well in the United States is less than 11.1 barrels per day. This is very typical. We ask things from the past. Are they still true today? This is a super, super common use of hypothesis testing. So we've got our mean from our 1998 level, which is going to be the one we're testing against, and we've got our sample. So our sample makes up our evidence, our sampling data, and then we've got our claim, and then we'll use that to form our null and alternative hypothesis. Since I have the standard deviation of the population, I can go ahead and call this a z, and pardon me, I need a drink. Okay, whew. And then we will reject this if it's a p-value that's smaller than 5%, and we will fail to reject if it's higher than 5%. So let's go ahead and shove this into Minitab. Stat basic statistics, we're going to do a one sample z. I'm going to have to use summarized data because my data is not in my worksheet over here. So I'm going to go ahead and plug this in. My sample size is 50 wells, and my sample mean is 10.7, and then my known standard deviation is 1.3, and my hypothesis value is, I think this is the old one, 11.1. And then I gotta check and change my alternative to being my less than option, and we'll see what the p-value is for this sucker. All right. So we get a z of -2. That's not too big. It's not too unlikely. But when we look at the p-value for that, it's actually pretty small. Now, this z isn't too far away. It's about 95% of all data if we're on the standard normal distribution. But remember, on the sampling distribution, we use a different standard deviation. This is our actual standard deviation for the sampling distribution. It's much smaller, which means the further you are away with a small standard deviation, the less likely she'll be. This is like, 15 times out of 1,000. That's not very likely. So we're going to be rejecting our h now because our p-value is just too small compared to 5%. And this is significant at the 5% level is another way to say that. I should have been saying that all along. Guess it pays to listen to the end. Suckers! All right. So there is sufficient evidence to support the claim that the mean oil output per well in the U.S. is less than 11.1 barrels per day. Good times. Let's do some more Minitab examples with stuff that looks like my stat lab. These are really hard to read. I apologize for this, but I literally screenshotted this shit. The study by researchers at the university addressed the question of whether or not the mean body temperature of an animal is actually 101.5 degrees. Among other data, the researchers gained a body temperature of 93 healthy animals. Suppose you want to use those data to decide whether or not the mean body temperature of a healthy animal is greater than 101.5. Complete parts A through C below. So we have an assumption that the mean body temperature is actually 101.5. We want to test that. We think it's greater. That's going to make our alternative. So I always do my alternative first because that's coming off the claim and I think it's a little easier to read. And then I set up my null as just the equal to version of that because that's what you need to be able to come up with the distribution. You need to have a mean. And clearly this is a mean test because we're talking about mean temperature, average body temperature. And then when you look at this, you're like, oh, I'm shading to the right. I'm looking at things that are bigger than 105. I know this is to the right because I think about the number line. So if like 105 was right here, I'm looking at things that are greater than it. That's to the right. So this is going to be a right-tailed test. I didn't want to click on that. So cadmium, a heavy metal, toxic to animals. It's pretty much toxic to everybody. Don't eat it. Mushrooms, however, are able to absorb and accumulate cadmium in high concentrations. Some governments have a safety limit for cadmium in dry vegetables, so if you eat lots of mushrooms, you'll die. Sadness. As 1.5 parts per million. That's what ppm stands for, by the way, not pineapple, pen, M? Metal? Mushrooms? I don't know. A hypothesis test is done to perform is decided. Wow, clearly did not write these. Thanks, my stat lab. A hypothesis test is to be performed to decide whether or not the mean cadmium levels of any certain mushroom is not equal to the government standards limits. Complete parts A through C below. Now you would think they'd be worried about you having more, but they care if it's different from in this example, which makes no sense. Thanks, my stat lab. Because heavy metal poisoning is not cool, and that's if you eat too much metal-y containing items. So, anyway. So, since they just say they want to say not equal to, it's going to be a not equal to for alternative, which means that there's our original, and therefore, since it's a not equal to, this is a two-tailed test. Alrighty. So in 1997, a survey of 902 households showed that 142 of them use email. Use those sample results to test the claim that more than 50% of households use email. Use a 5% significance level to test this information for the following. So we actually think it's greater. More than is what cues you in on that. So none of these are an option. Well, you can eliminate E immediately because, well, not E, sorry. Where is it? A and C, because they both have like alternatives that are, nulls that are not zeros. Same thing for D. So your options are like B, E, or F, and we know it's not a two-tailed test because they said more than. So this is either this one or that one. Well, this is only stuff that's more than 15%, so it's definitely F. All right, and we're going to use Minitab to come up with these test statistics. So stat, come on, basic statistics, one proportion. Oh, I know this is proportion because it gives you a number of households sampled and number that were successful. So 142 out of 920. And I'm testing this against 15%, and my options are I want it greater than, oh, it's already set up right. Let's hit OK. Let's hit OK again. And there's our Z value and our P value, so we'll go ahead and put those in. And these are rounded correctly, but make sure you watch your rounding should you need to round more for this guy. All right. So what's the proportion? Or what's the conclusion? Hey, there's not sufficient evidence to support the claim that more than 15% of households use email because my p-value is freaking huge. 35.6%. It's enormous. Anyway, is the conclusion valid today? Well, no, clearly. I mean, it's got to be more than that, right? Because the characteristic we're seeing for the emails has been changing, well, rapidly. You know, it's completely ridiculous. Anyway, I really like number 9. I might remove number 9 next year. Anyway, let's do number 10, and then peace out, homies. A not-for-profit company is concerned with high school dropout rates in a nearby state. This is so vague. In a nearby state has designed a tutoring program aimed at students between the ages of 16 and 18 years old. The high school dropout rate in the state in the year 2000 was 10.8%. Their programmer should have just replaced in a state with a random selection of the 50 states. And then this would make more sense. But no, they didn't, because evidently they can't do that. Anyway, so one school district who adopted the use of the not-for-profit tutoring program and whose dropout rate has been very close to the state average, reported in 2004 that only 184 of their 1,778 students dropped out. Their experience evidence that the tutoring program has been effective? Explain. Wow. Okay. Sorry about that. I read that terribly. Hopefully you're reading this and just like fast forwarding through my junk. Anyway, so the null and alternative hypotheses, check them out. So we're checking this against the year 2000 rates to know if 2004 looks different than 2000 in the year 2000. So we're going to use that 10.8% to form our claim because we're thinking, is it their evidence it's been effective? Effective would mean that the dropout rate has gone down. So our claim that we're going to be testing is that, P is actually smaller than 10.8. So we want to look for that. And there's only one of those. So that pretty much narrows this down. Yay! It's B. Done. Now let's calculate the rest of this junk. So I'm going to go up to stat, basic statistics, and one proportion. I'm going to put in my data. So 184 of the 1,778 people. And I'm testing this against 10.8. Check my options. My alternative needs to go the other way, otherwise it'll calculate the wrong P. It's very important that you actually change this if your alternative is like that way rather than the other way, because otherwise it produces the wrong P. Actually, maybe I'll show you that after I do this. Hold on, hit OK. Hit OK again. There's the correct one. There's our Z, and there's our P. But let's suppose you made a boo-boo. I'll prove to you that this actually produces a different value. Like, oh no, I put in the wrong one. Oh no, it's the wrong values. Here's something worth noting. So I just did the not equal to test instead of the less than test. This is kind of fun. It's the same Z. Why are the P's different? Because remember that the alternative determines the direction in which you shade or the area that you get. This is one-sided, this is two, which means it's going to the left and to the right, and this is only going to the left. So as you look at this, my lovely children, I'm hoping you notice that this p-value is double that p-value because you're getting twice as much. Both tails, one tail. Two tails, one tail. Makes sense, right? Maybe you didn't believe me before when I talked about this in the lesson, but maybe you do now because the computer told you so. Anyway, so that's a pretty large p-value. We're probably rejecting. Oh, I'm sorry, we're failing to reject because this is pretty likely. So since the p-value is greater than 5%, we fail to reject. There is sufficient evidence to determine that there was a decrease from the dropout rate of 10.8. If you look at the other fail to reject, it says there is sufficient evidence to say that it's decreased, but that's not what we got. We've got something that says that you can't say it's different, so we're failing to reject the idea that it's that. So it's like rejecting the wrong hypotheses. So that's why it's not C. Wait, not C. Wait, D. That's the one I was talking about. Sorry, I said the wrong one. All right. Hope you enjoyed. Bye.